Hello everyone, this lecture is about stress and rheology. Last week I've introduced the question about Earth rheology. So what is actually needed to describe the Earth constitutive behavior? On the one hand, we need the rocks to be elastic. This allows seismic wave to travel through the Earth. On the other hand, the rocks should be viscous on the long tectonic deformation timescale and to allow also for mantle convection. So rocks should be able to flow or creep in order to record permanent deformation, and the mantle, for example, should be able to convect in order to induce plate motions, for example. Another thing which is needed in terms of rheology, you know that we have plates and that these plates are surrounded by zones of high deformation. Since the deformation is localized into narrow zones in most cases, we also need to be equipped with a plastic rheology. A plastic rheology is a mechanism that will allow the localized deformation at plate boundaries. So one needs elasticity, one needs viscosity, and one needs plasticity. So the Earth should be a viscoelastoplastic medium. Last week, we've discussed about the strain and the strain rate. The conclusions were that the strain tensor and strain rate tensor, they allow to quantify the kinematics of deformation. We have deformation that can lead to a change of shape, deviatoric strains, and deformation that can lead to a change of volume, volumetric strains. And that these tensors can be split into volumetric and deviatoric parts. So we've worked on these different points. Now what we want to do in this lecture is to make a step towards the evaluation of stress. So let's take a basic example here. What is a stress? A stress is a force which is exerted through a surface. So on one hand, you have a person standing on high heels. On the right side, you have a person standing on very large shoes. So now let's evaluate what is the unit of the force. You should all know that the unit of force is the Newton. Since the stress is a force exerted through a surface, the unit of stress is a Newton divided by square meter. This is called a Pascal. So now let's think about these two persons, and let's assume that these two persons, they weigh the same mass, 70 kilo for each person. These two persons are inside the same gravity field, so they feel the same gravitational acceleration. The force induced by the body of the person is mass times g, 700 newtons. Now, let's compute the stress. Once again, the stress is the force divided by the section over which the force is applied. So, stress, force divided by area in both cases. Now, one of the shoe has a high heel section of 1 centimeter square, while the snowshoes here have a section of 1000 centimeters square. The difference is, of course, of 3 orders of magnitude here. So the person with high heel would exert a stress of 7 megapascal, while a person with snowshoes will exert a stress of 7 kilopascal. So this is 3 orders of magnitude difference. And this is very important This is a fairly huge number here. And indeed, you can realize that if someone walks with high heels in your house, it may leave some traces on the wooden floor, for example. So the high stress can induce deformation. That's the case for the floor, but that will be the case for any material, including rocks. On the other hand, if the stress is low because it's distributed over a large section, then the magnitude here is low and there is few deformation here. You are not sinking into the snow. So this magnitude of stress drives deformation and stress matters. So that is an example here of application of this in a very applied case. It's also tightly coupled to reactions in rocks and materials, and this is an example of stress-driven corrosion of cooling system in power plants. So stress matters in geological systems, but also, of course, in engineering technology. And it is linked to mineral reactions. So let's talk about the stress tensor now. So we had a strain and a strain rate tensor last week, and this week we introduce a stress tensor. So let's make a little sketch here. There is a coordinate x1, x2, x3, and a cube here. And you see on this cube there are tractions which are applied. So there's a traction applied in that direction here on that face. A traction 2 is applied on a face which is normal to axis 2, and traction 3 is applied on the face which is normal to axis 3. So these tractions are vectors, and these vectors have 3 coordinates in 3 dimensions. So for example, T2 here can be split along the 3 axes of the space. So T2 projected on x1, T2 projected on x2, and T3 projected on x3. So the traction is a vector. In 3D, it has 3 components. Now, if we consider the 3 traction vectors, each of them can be projected along the 3 axes of the space. So T1 here, T2 here, and T3 there. So we have 3 tractions, and each of these traction vectors have 3 components. So let's gather these 3 traction vectors into a single object, and this will become our stress tensor. So a tensor here can be perceived as a vector or vectors. So using the index notation here, we can formulate the stress tensor as sigma 11, 12, 13 up to 33 for the 3-dimensional case. Alternatively, you can use the x and y notations to populate your your tensor. So when we know the stress tensor component, we can evaluate the traction which is applied to any arbitrary surface into the material. So now you can think about your 3-dimensional axis, and now we take a cut, an oblique cut through the 3-dimensional material, and there will be a normal to the face. The face is defined by the normal, and if there is a traction vector, it can be computed using the stress tensor and the normal. So to compute the traction, we set it equal to the product of stress times the normal of a face. So let's work in 2-dimensional. So you see here an xy coordinate system. We have a square here, and on each of the faces of the square, we have stress tensor components, which are highlighted, sigma xx along x, sigma yy along y. These are the normal stresses. Sigma xy along this face here, and sigma yx along the horizontal face. So in 2 dimensions, we have 4 components here. And again, the traction is the stress times the normal. So let's evaluate the traction in the x direction. So we formulate n has 2 components, x and y. And in the x direction, the normal n has 4 components, 1 and 0. It is aligned with the x-axis, and it is a unit normal. So it's 1 and 0. And let's do the product, sigma times n. Sigma times n is sigma xx times 1 plus sigma xy times 0. This makes sigma xx. Now we go to the second line, sigma xy times 1 plus sigma yy times 0. This makes sigma xy. Now we do the same exercise, but for a vertical normal. So a normal which is perpendicular to the horizontal plane. So now the unit normal has 2 components, x and y. The x component is 0, and the y component is 1. If we apply the same product, stress times normal, we will obtain a vector of sigma xy and sigma yy. So what we can see here is that if you create a vector with your 2 traction vectors, so we put them together, we will retrieve the 2D stress tensor. Another funny exercise that we can do is to evaluate now a traction in an arbitrary direction. So we now cut our 2D square, and we have a normal vector, which is normal to this face here. It has 2 components, an x and an y. So we apply the product, and we get to this situation where, of course, an x and an y are not given as numbers. We cannot simplify this expression. It's still a vector. If we rotate the coordinate system, something interesting will happen with the stress tensor. The magnitude of the traction will not change. So we have the xy coordinate system and this situation where a face is being cut oblique through our square, and we will have a case where the coordinate system is rotated. But we have exactly the same situation. You understand that the traction here is the same as the traction in this case. It should not be depending on the orientation of the coordinate system. So we can quickly do this example. So if we compute the traction in this coordinate system, we have t is equal to sigma times n. In the rotated coordinate system, we have x prime, y prime, and we formulate t prime is equal to sigma prime times n prime. So let's compute this. We will now apply a rotation of the coordinate system to compute t prime. So let's compute t prime. This is equal to r, the rotation which is applied to the coordinate system, times the original traction vector t. Now we do the same for the normal. So n prime is equal to r times n. Now we formulate n, so we can solve for n, and you obtain n is equal to r minus 1 times n prime. This is also equal to r transpose times n prime. In the next step, we substitute this definition into the line above. So T here is replaced by sigma times n, and n is replaced by r transpose n prime. So one obtains this object here, and one can identify that r times sigma times r transpose has to be equal to sigma prime. This is equal to that. So that's the formula for the rotation of, or the expression of a stress tensor in a rotated coordinate system. So the rotation matrices are orthogonal, so that determinant of r is equal to 1. And all the norms of the magnitudes of sigma, the invariance of sigma, will be independent on the coordinate system. So that's a special feature of the tensors. They have to be objective. So now, how does the stress tensor relate to the deformation we introduced last week? So we need to introduce the definition of a constitutive model. So the constitutive model is a relationship between the strain or the strain rate and the stress. In elasticity, we have one constitutive relationship for elasticity. There will be one for viscosity, which can explain continuous and permanent deformation. And we will need also to formulate the effect of plasticity on the constitutive models. Plasticity will be the mechanism that will allow to localize deformation, such as in fault zones or shear zones located at plate boundaries. In elasticity, you know that the waves are traveling through the medium, but they are also leaving the medium undeformed. Once the wave has passed through the medium has recovered its original shape. So elasticity is reversible. It involves very small strains, and during elastic deformation, the energy is stored and it is recoverable. There is no entropy production linked to elastic deformation. Elasticity is a function of strain. So that's another example. Here you see someone stretching a rubber. You can stretch the rubber, but what matters is how much you stretch it. The more the rubber is stretched, the harder it becomes. The stress increases in the rubber band. So elasticity affects both shear and volumetric deformation. So we have P waves and S waves that can travel through rocks. There is no dependence on time. So it's seen as a time-independent mechanism of deformation. The rate at which the deformation takes place has no effect. It does not impact the magnitude of stress. That would be a pure elasticity aid. The stress will only depend on the strain. And remember, last week we had introduced this tensor, the deviatoric stress tensor, in 2 dimensions with 4 components here. There will be a stress tensor a deviatoric tensor also, which will be associated to deformation. And how to formulate the relationship between stress and strain rate? We will use a coefficient matrix here that is diagonal for deviatoric deformation and contains the shear modulus, G. Equivalently, one can write this expression, sigma xx deviatoric is equal to 2 times G times epsilon xx. Sigma yy deviatoric is 2 times G times epsilon yy, and sigma xy is 2G epsilon xy. So what's the unit of G? Remember that epsilon xx has no unit. Stress is unit Pascal. Therefore, G has to be unit Pascal. In elasticity, there is also non-zero volumetric component. So one can relate the volumetric stress to the volumetric deformation. This is the definition of the pressure. And you see that the pressure is related to epsilon vol, which we learned to compute last week. There is a coefficient of proportionality between P and epsilon vol, and this is the bulk modulus. Once again, what's the unit of K here? The volumetric strain has no unit. P is pressure, so it has unit Pascal. K has to be unit Pascal. Now, in the case of viscosity and creep, the deformation are irreversible. So at the end of the orogeny, the rocks keep on being folded. They do not unfold. This is shown by very large strain on the field. And with this type of deformation, the work is dissipated. So another type of viscous material that you may know is the pitch. That's a byproduct of oil production. It's an extremely viscous liquid. And other types of viscous materials can be can be found in your kitchen. So the cheese fondue is a viscous material, and the viscosity there depends on the temperature. In a viscous material, the stress increases not as a function of strain, but rather as a function of the strain rate. So if you would stir the cheese fondue very, very fast, it would become more and more difficult to stir it. The viscosity affects mainly shear deformation, and it's often assumed to be incompressible. There's a dependence on time in viscous flow, so the rate at which a deformation takes place matters. So not only pitch and cheese fondue are viscous materials, but rocks can also flow or creep. That's a superb example from a slab of rock that has been under gravity for, I guess, several centuries. And you see that this plate is being deformed progressively with age. And this is an irreversible deformation. And it is not localized. So that's an example of flow or creep in rocks. How does it work now? We want to relate stress to deviatoric strain rate. That's how stress related to viscous flow can be quantified. So on the one hand, we have the deviatoric strain rate introduced last week, and on the left side, we have the deviatoric stress. We want to compute the stress as a function of the strain rate, and we introduce again a constitutive matrix here, which is fairly simple for an isotropic material. You have 2 times eta on the diagonal. Eta here is the viscosity coefficient. Equivalently, one may express this relationships. Sigma xx deviatoric is 2 times epsilon dot xx, and so on. So what's the unit of eta? Remember that the deformation has no unit, but a deformation rate has a unit of 1/second. Stress has unit Pascal, therefore eta needs to be of unit Pascal times second. Usually the viscous deformation has a negligible volumetric component, so the pressure cannot be defined solely by the rheology in a viscous fluid. So we mostly keep on going with the definition of the deviatoric stress. Now going to plasticity. Plasticity is a mechanism that allows the localization of deformation in rocks and the accumulation of large strains. That's a fantastic example of the Glarus thrust fault, and it's a super manifestation of strain localization. So you see 2 different colors of rock, and in between there is a sharp boundary. This is a fault. On top you have old Permo-Triassic rocks, and below you have younger Jurassic and Cretaceous rocks. So these rocks have been brought up on top of the younger ones. The deformation is extremely localized into a narrow zone. So the rocks had to localize in an extreme manner. In a way, it had to break. So the plasticity leads to localized strains and material failure. Another example here, think about jumping on a board. If you jump on the board will deform, but if you jump too high and you exert too much stress on the board will break and you will fall. So the plastic deformation is an example of irreversible deformation. Once the board is broken, it cannot glue back. It can lead to large strain, and again, the deformation work is dissipated during plastic deformation, and entropy is produced. So one can represent the evolution of stress with strain using a stress-strain diagram. That's an example here. So you have on the axis here a measure of the stress, for example, one component of stress, versus another measure here, which is the strain, for example, the one component of the strain tensor. In the elastic regime, the strain and the stress are linearly related. So the more the plate is strained, the larger is the stress in the plate. So you bend the plate a little bit, the stress increases a bit, you bend it more, it increases more, and so on and so on. And at some point, the stress reaches a high level. What happens? It will reach a level at which the fracture or the material yielding will take place. And then the board will break. So what plasticity is doing is implicitly introducing a limitation of the stress. It is a maximum stress beyond which the material will fail. And that's, of course, the case with rocks. So in a way, plasticity theory builds on top of elasticity and viscosity theory. It is an upper bound limit of stresses. So if the stress predicted by an elastic model is too large, then there will be failure. If the stress predicted by a viscous model is too large, there will also be failure. So that's some example of results of analog rock deformation in the lab. So you have examples of capsules that contain rock material and that have been deformed in the laboratory. So you see here a torsion experiment, and you see that the rocks can record very large strains, and this is also associated to a variation of the stress. In the different types of apparatus, you can also model fracturation of the rocks and faulting. You can also see that under some condition, the faults can disappear or can become more and more diffuse. So to go from localized deformation to less localized until going completely ductile, where the deformation is permanent but distributed. So in plasticity, one often uses this relationship for rocks, and this is called a frictional law. This is the friction law introduced by Byerly in 1978. And what the author did, he plotted together. So he collected a lot of experimental data and he plotted the measured shear stress versus normal stress applied to the experiment. So you can apply a normal stress to the sample, for example, to one of these rocks here, and measure at which shear stress the rocks will break apart, basically. So what he realized is that the maximum shear stress depends linearly on the normal stress, and that for most cases here, these different points, they correspond to different types of rock. So the different types of rock, they can be fitted with a single line. So for low to moderate normal stress, this law is rock independent. And it can be formulated. So here you see one expression is that tau, the shear stress, is equal to C plus tangent phi times sigma, where sigma here is the normal stress. So C will be the constant, the intersect of the line, the red line with the vertical axis. It is called the cohesion. Phi is related to the slope of this line, and it is the friction angle of the material. In an intact rock, the cohesion is about 50 megapascal, and the friction angle is about 35 degrees. Remember this measure here, 50 megapascal, so that's really for a stiff rock. But the megapascal scale, we've seen it before, it is the same scale as when someone is walking with a high heel and weighs about 70 or 80 kilos. So we are very close to this order of magnitude of stress that can cause yielding of the materials. So plasticity can be seen as a critical stress level that will control the activation of localized deformation within the rock mass and through the plates. So it can be used to explain the faulting and plate boundary formation. So the summary, we have elasticity, and in elasticity the stress relates to the strain, and we have introduced the shear and the bulk moduli to quantify the magnitude of stresses. We have reversible and small deformation, and this model may be used to study the propagation of waves in the earth, for example. The viscosity, it relates the stress to the strain rate. And we have one coefficient, it is the viscosity coefficient. Usually deformations are mostly incompressible in the viscous realm. They are irreversible and they can lead to large strains. And in the plastic realm, there is a stress limiter, and beyond this stress limiter, failure occurs. So this leads to localized deformation, irreversible deformation, and large strains. Also, we've seen that the stress limiter here depends on the normal stress. So the higher the normal stress, the higher will be the resistance to frictional yielding. Thanks a lot for your attention.